All right, example 3, the access to sketch the function f of x equals to x times e to the power x. All right. Now, as usual, the first thing you need to check is the domain. Okay, in this question, I say the domain is x element of a real number. Let's see why. First thing is this is a product of some linear function. You can say polynomial with the real one, and some exponential function. And you know that exponential function, the domain is just a set of real numbers. So if you have the product of two functions where their domains are the set of real numbers, therefore the domain of the product of the two functions will just be the set of real numbers. Intercepts, if you set x to be 0, notice that you have 0 times e to the power 0, which is just 0, all right? So again, your graph needs to pass to the origin. Let's look at symmetry. So you say f of minus x. If I replace x with minus x, what happened? I end up with minus x times e to the power minus x. Notice it doesn't look like my original function, and it doesn't look like minus my original function. So we say there's no symmetry. All right, you can say neither odd or even, or you can just say no symmetry. All right, horizontal asymptote, if you take the limit as x tends to, let's start with minus infinity. Remember that this is one of the indeterminate form when we did L'Hopital rule. So if you have minus infinity times 0, remember that e to the power minus infinity is just 0. All right. Let's see if we can demonstrate various cases. Remember, e to the power 0 is 1. You know at 1, that curve, that's how the shape looks like. So you see that when you oppose minus infinity, your curve is getting closer and closer to 0. So in this case, the limit is x tends to minus infinity. It's just the same as just saying minus infinity times 0. And that is an indeterminate form. So we can apply L'Hopital rule. To apply L'Hopital rule, you need to rewrite it so we can keep the x at the top and then take the e to the power x to the bottom. Notice if I substitute that minus infinity, I have minus infinity divided by e to the power minus infinity, which is e to the power infinity. Therefore, I have infinity over infinity, and hence we can apply L'Hopital rule. Remember, before you can apply L'Hopital rule, you should be able to get your limit to equate to 0 over 0 or plus or minus infinity over plus or minus infinity. So in this case, if we apply L'Hopital rule, you differentiate the top, you just get 1. You differentiate e to the power minus x, you have minus e to the power minus x. And if you put in the limit as x tends to minus infinity, it's just 1 over some infinitely large value, which is 0. All right. Now we now look at the limit as x tends to infinity. Obviously, you see that you have infinity times e to the power infinity, which is just infinity. All right, so there's nothing we have there. Therefore, the only asymptote or horizontal asymptote we have is y equals to 0. All right. Remember, infinity times infinity is not an indeterminate form. So please revise section 4.4. See what the indeterminate forms are for those of you that have forgotten about L'Hopital rule. And then there's no vertical asymptote. Remember, vertical asymptote means there's some restriction in your domain. In this case, yes, there's no vertical asymptote because x is an element of real numbers. So look at the domain that we have here. This domain tells that we don't have any restriction, therefore we can have a vertical asymptote. All right. The next thing is increasing, decreasing. Obviously, you find your first derivative. If you equate this to 0, notice that this function here, e to the power x, can never be equal to 0. So if you equate it to 0, you're just looking at 1 plus x equals to 0, where x is minus 1. All right. That will be your only critical value you have to work. Obviously, some of you say, where's the function defined? So look at this. The first derivative function is defined for the set of real numbers. All right. So in that case, it will be defined everywhere. So there's no need to try and find critical values for which the first derivative is undefined because this is defined everywhere. Now at minus 1, obviously you test the sign. So if I choose minus 2 on the left, you see it's negative. Hence we have that decreasing. On the right hand side of minus 1, I can choose 0. If you plug in 0 in your first derivative, remember I'm still reminding you that you're substituting in your first derivative. you get increasing, right? Therefore, you see the decreasing happens from minus infinity to minus 1, and increasing happens from minus 1 all the way to infinity. Straightforward and easy. All right, what's the next thing? The next thing obviously is going to be concavity, and by now you should be familiar with concavity. What do we need to do when we're doing concavity? We need to find the second derivative, right? Very, very important. You need to find the second derivative. But before doing that, let's see, we need to see if we had any turning points. Notice that at minus 1, you have a change of sign from decreasing to increasing. That tells you that there is a local minimum at that point. All right, don't just tell me that there's a local minimum at minus 1. Write it in this form. So f of minus 1, plug it in your function, it gives you minus e to the power minus 1. All right, and you say that is a local minimum, all right, because you see there's a change of sign there. For concavity, we find second derivative. This is a nice function to differentiate. So you see, you can easily factor out e to the power x as well. Again, this is equals to 0 only when x equals to minus 2. And if you test on the left, you have that this concave downward, it means you will get a negative sign. And if you test on the right, you get concave upward, I mean they have the positive sign. And as usual, I'm reminding you that you're testing using the second derivative function. Concave up, obviously concave up is this piece here, this side, so it's from minus 2 to infinity. Concave down is from minus infinity to minus 2. It's as easy as that, right? And then, do we have any point of inflection? The answer is yes. I'll show you now. Look at it at minus 2. Remember, for inflection point, you look at your concavity. So after finding second derivative, I'm putting that on a normal line. If there's a change of concavity, so from concave down to concave up, it means that this minus 2, x equals to minus 2, we have a point of inflection. But now, actually, if it's minus 2 part of the domain, that's a question you always need to ask. Is minus 2 part of the domain of the original function? The answer is yes. It means I can say f of minus 2, which is just minus 2 times e to the power minus 2. It's an inflection point. All right. Here I'm just trying to explain. Since there is a change of sign, you don't have to explain that there's a change of sign. Just tell me where the inflection point is. And obviously, to sketch it, first thing you notice is your horizontal asymptote there was y equals to 0. Remember, y equals to 0 is just this x-axis. So you indicate your horizontal asymptote. There's no vertical asymptote. Now, what else do we know? We know that it passes through the origin. So you mark that point there. So that's your intercept. It passes through the origin. And then look at concavity. We see that we want it to be concave up from minus 2 all the way to infinity. So from minus 2 all the way to infinity, it has to be concave up. And we want it to be concave down from minus infinity to minus 2. So that tells you that at minus 2, remember that at f of minus 2, where you solve for this inflection point, that helps to tell you where there's a change of concavity. Hence, the reason why I always want you guys to evaluate the function at the x value. Don't just say an inflection point at x equals minus 2. Solve it, find f of minus 2, because it's useful when you sketch it. You see that f of minus 2, that is my inflection point. Inflection point is important to note on your sketch, because at that point there's a change of concavity. It becomes easy for you to sketch. On the left hand side of minus 2, look at what happens. I have concave down. So I'll have a shape that looks like this, and it gets closer and close to my asymptote. It doesn't touch it, hence you see that shape. On the right hand side, what do we have? We have concave up. So I know that from there, we're going to have something that looks like this. All right. And why is this point also important? That was where you had your turning point, right? Remember, you had the local mean at x equals to minus 1, right? So that turning point happens at this point here, and it passes through the origin. There you go. That's your shape. All right. So please practice and get comfortable with such kind of example. Let's look at 4 quickly. 4, we get back to trig function. The domain of this trig function, you want this bottom piece to not be equal to 0. So you want this bottom piece to not be equal to 0. But what does that mean? It means that sine x cannot be equal to minus 2. All right. But ask yourself the question, can sine x give you minus 2 in the first place? The answer is no. So in summary, we just have x element of real number. I'm going to explain why. Remember, the sine and the cos function, they lie between 1 and -1, all right? So sine x cannot give you -2 in the first place. It means you don't have any restriction, all right? Hence, x is just element of real number because there will not be any x value such that that bottom piece will be equal to 0, such that sine x will be -2. Let's look at intercept. If x is 0, you just get the 1/2, all right? So cos of 0 is 1. At the top here, you're just going to get 1. And at the bottom, sine of 0 is 0, so you have 1/2, which is half. Now, when y is 0, you need to equate this whole thing to be equals to 0. Remember, the only way that can be equals to 0 is if the top piece is equals to 0. Very important. So indirectly, you're solving for cos x equals to 0. And you know for every multiples of power over 2, I can say odd multiples of power over 2, you're going to get 0. So for example, if x is power over 2, you know cos of 90 is 0. Another odd multiples of power over 2 is 3 power over 2. Again, you get 0. Hence, I just gave you that formula there. For every 2n plus 1 times power over 2, you're going to get your function to be 0. All right. Let's look at symmetry. F of minus x. We know that cos of x is an even function, so cos of minus x will just be cos of x. But what happened to sine? Sine is an odd function, so sine of minus x is minus sine of x. If you look at this, this doesn't look like my original function because it's a change of sign here. And it doesn't look like minus f of x as well, so there's no symmetry. All right. Is there any horizontal asymptote? What happens if you take limit as x tends to plus or minus infinity? All right, this doesn't give you any result. I'm going to explain why. Because it's a periodic function. The sine and cosine function, it doesn't approach a specific number irrespective of how much you increase x. So there's no horizontal asymptote. So the answer there is that the periodic function, meaning that they just keep continuing forever. They oscillate between 1 and -1, so hence it doesn't really help you. It doesn't converge to a particular number. And there is no vertical asymptote as well. You know why? Because look at what we had in the beginning. We say x is an element of real number. It means that there is no restriction. All right. First derivative to find increasing, decreasing. So if you solve, simplify, always simplify as much as you can. You see I had to group the sine square and cos squared so that I can use the identity that is equals to 1. All right. And that makes my life easy. Then I can find my critical value, which is when is this function equals to 0? If you equate this to 0, the first possibility you're going to get there is that your reference angle is pi over 6. Now, when is the sine function negative? So I'm just going to draw this little quadrant diagram there. You see that there is a problem, or sine is negative in the third quadrant and the fourth quadrant. That's why you see I'm focusing on the third and the fourth quadrant. Looking at that quadrant diagram, I know that tan or sine is negative in the third quadrant and the fourth quadrant. And you just need to ask yourself, what's the formula that we use in the third quadrant? Is pi plus reference angle. So you just take pi plus pi over 6. And then for the fourth quadrant is 2 pi minus reference angle. There you go. So you have 7 pi over 6 and 11 pi over 6. All right. There you go. You put them on your number line. So you have 7 pi over 6. That's 11 pi over 6. You test the interval. Notice that I focus from 0 to 2 pi. Remember what I told you before? Whenever I give you a trig function in the test or in any way when you're dealing with my calculus 1, it's from 0 to 2 pi unless I tell you I give you a different interval to work with. So in this case, stick to the normal interval, which is from 0 all the way to 2 pi. All right. So in that case, if you test, we can choose between 0 and 7 pi. We can choose pi, and between 7 pi over 6 and 11 pi over 6, you can choose 7 pi over 3, and so on. All right. So just test the sign, and as usual, make sure that you put in the first derivative. So this is one of the exciting examples that requires you to do a lot of work. All right. You can see the sign there. Here is negative, here is positive, and here is negative. All right. So for increasing, you only have one interval between 7 pi over 6 and 11 pi over 6. For decreasing, you have two intervals from 0 to 7 pi over 6 and from 11 pi over 6 to 2 pi. And that's what happens in the next slide. So please make sure you can do stuff like this. And obviously, you're going to get a turning point. Why? Because look at, let's just go back quickly so that you see why there is a turning point. Now, if you look at the increasing, decreasing, here you have decreasing, and here you have increasing, and here you have decreasing. Remember what I told you, once you change from decreasing to increasing, it means you have a local mean. When you change from increasing to decreasing, you have a local max. So you see in this case, you're going to get a local mean as well as a local max, right? Because of the change from increasing to decreasing. All right. And that's just what so f of 7 pi over 6, notice it is 1 over root of 3, it's just a local mean. Then f of 11 pi over 6 is 1 over 3, and this is a local max. All right, so you have both local max and local mean. Then you need to go and solve for second derivative. Again, differentiate, simplify as much as possible. So from this first derivative, you need to find, I'll just indicate there, you need to find f double prime. All right, so that's what I'm doing there, just applying quotient rule to find the second derivative. And you end up with something that looks like if you simplify as much as possible, right? So simplify as much as possible. If you equate it to 0, this whole thing is equal to 0 only when the top piece is equal to 0. So you have cos of x equals to 0, and then 1 minus sine x equals to 0. All right? And if you notice it, you have a lot of values. There, cos of x equals to 0, you have pi over 2. And in quadrant 4, it also applies, which is 2 pi minus pi over 2. All right. Why am I having two quadrants? You need to ask yourself, in what quadrant is cos positive? It's in the first quadrant and the fourth quadrant. So in the first quadrant, is pi over 2, and in the fourth quadrant, we use 2 pi minus reference angle, which was pi over 2. And then for 1 minus sine x equals to 0, it just equals to sine x equals to 1. When is sine x equals to 1 is when x is pi over 2. And remember, sine x equals to 1 means sine is positive. When is sine positive? First quadrant and second quadrant. So these numbers you see here is just a quadrant. I'm referring to the quadrants there. So in the first quadrant, you have pi over 2. In the second quadrant, you use pi minus reference angle, which is pi over 2. Notice it's just the same values there. All right. So in this case, how many critical values do we have? Notice it's only 2. Is pi over 2 and 3 pi over 2, because this one is just the same thing. It's just pi over 2. You can now go and list pi over 2 so many times. It's just two critical values that we have to work with. All right. So there's nothing wrong when you get the same value for x. At the end of the day, just group them. So those that are the same, just use just one of them. All right. In this case, we use pi over 2 and 3 pi over 2. Look again, there's a change of concavity from concave down to concave up, and then we have concave down again. All right. So obviously everyone knows how to state this, and I'm reminding you that you're testing using your second derivative function. You see that you're going to get two inflection points at pi over 2, because you see there's a change of concavity, and at 3 pi over 2. The domain of our function was the x element of real number. It means that definitely the function will be defined at x at pi over 2 and 3 pi over 2. And in both cases, you just get 0. All right, it's fine. So there you go. And for this case, notice we didn't have any horizontal vertical asymptote, but we had intercept. So you knew where it cuts this coordinate axis, and you also know where it cuts there on the y-axis. All right. And in terms of concavity, notice it between pi over 2 and 3 pi over 2 is concave up. Hence, you have that nice shape there. And how do you know where this turning point happens? This turning point happens when we did increasing, decreasing. At increasing, decreasing, we said there was a local mean at this point here, which was 7 pi over 6. All right, there you go. And then, so you're able to do this. Now, you know that the only way to link this point and this point is by doing that, all right? And if you're not sure that that is the case, look at where you have concave down. Concave down is from 0 to pi over 2. It means that from here all the way to pi over 2, you're going to get that kind of shape, all right? And then I have another concave down from 3 pi over 2 up to 2 pi c. There we go, from there all the way to 2 pi. And then where is that peak there? That peak, you notice it, we had a local max when we're decreasing, and that local max that will give you that value. And you're done. You see, every single thing is important. Your intercepts, your concavity, where you had your local max and local mean, they're important because they give you the turning points. And there you go. And that's all for this question. Is there any question before I continue? All right, it looks like everyone is happy. A straightforward example. Let's look at this easy one. Say sketch y equals to ln. So now we're going to a logarithmic function. Remember, for a ln function, everything inside the ln function has to be greater than 0 for that ln to be defined. All right, ln of 0 is undefined, or ln of a negative number is also undefined. Therefore, everything inside the ln function needs to be greater than 0. Hence, you're just solving the inequality x squared minus 4 is less than 0. And if you solve that, you just have x lies between minus 2 and 2. That's your domain. So x lies strictly between minus 2 and 2. All right. For intercept, if you set x to be 0, you just have ln of 4. All right. And if you set y equals to 0, you're solving this whole thing equals to 0. Remember that ln is the same as log to the base of e. So you're going to have 4 minus x squared is equals to e to the power 0, which is 1. All right. And you end up with x squared equals to 3. X just become plus or minus root of 3. All right. And this value is fine because look at our interval. The domain is from minus 2 to 2. You know, root of 3 is typically just 1 point something. So it's fine. It falls within the domain. And minus root of 3 is minus 1 point something. Again, you're happy. It falls within the domain. All right. If not, I was just going to ignore some of the x values if they fall out of the domain. Symmetry, what is f of minus x? Notice it looks like our original function. Therefore, you say it's even. All right. Let's look at asymptotes. Horizontal asymptote, if you take the limit as x tends to plus or minus infinity, you see that this case is approaching minus infinity. All right. And for vertical asymptote, we're now focusing on where we had those restrictions. Remember, those restrictions happen at minus 2 and 2. All right. If you look at the domain, the restriction or the endpoints were at 2 and minus 2 that were not included. So we focus on 2 and minus 2. So you take the limit as x approaches 2 from the left, the limit as x approaches minus 2 from the right. So just test and check the signs. So, and choose values really close to this. So if I say 2 to the left, so I'm looking at something like 1.9. And 2 to the right, I'm looking at 2.1. All right. So do that sensitively. Now, if you notice here, I'm only testing 2 possibilities. I'm going to explain why. I'm testing 2 from the left, and I'm testing minus 2 from the right. Why? Because look at how my domain looks like. All right. My domain is from minus 2 all the way to 2. So this means that I cannot test 2 from the right. You see, I can only test 2 from the left. Because 2 from the right, I need to have something like 2.1. But you see, it will not be part of my domain. Also, for minus 2, you cannot test minus 2 from the left. Because you cannot have any value smaller than minus 2. It's not part of your domain. You see, there's only 2 things you need to test there. 2 from the left and minus 2 from the right. Because of your domain. I'm doing this just so that you get used to the fact that your domain is very important. Everything you do, go back and reference your domain. Look at your domain. Your domain will guide you. And then the conclusion is that x equals to plus or minus 2. Those are vertical asymptotes. First derivative is straightforward and easy. Just apply your product rule. In this case, it's chain rule actually. So the ln is 1 over the function times the derivative of the inner function. All right. And you get something that looks like this. Critical values, when is it equals to 0? When the top is 0, so x is 0. When is it undefined? When the bottom equals to 0. In that case, you have minus 2 and 2. So You have 3 critical values to work with, minus 2, 0, and 2. Notice it, I'm only testing this interval here and this interval here, all right? You don't look at anything on this side or on this side of 2. Why? Because your domain restricts you. If you choose any value bigger than 2, you try to plug in your link function, will be undefined. If you choose any value smaller than minus 2, it will be undefined as well because of your domain. Very important. The domain helps to guide you to see where you're going to end, your endpoints are. All right, there you get increasing. So increasing there, and then you have decreasing there. Already you can see there's a local max at x equals to 0. You see, before we even get there, we can see there's a change of sign from increasing to decreasing. Therefore, there's a local max there. So state your interval for increasing, decreasing, and you say f of 0 is just linear 4 is a local max. All right, very easy to observe. Now we need to discuss concavity. Obviously, find your second derivative, simplify as much as possible. When is it equals to 0? Notice it, this top piece here. If you equate it to 0, what do you have? You end up having minus 2x squared equals to 8. You end up with x squared equals to minus 4. Notice that there's no solution there. So it can never be equal to 0. However, there is critical values for which is undefined when the bottom piece equals to 0. All right. It will be undefined when the bottom piece is 0. In that case, you get your critical values as minus 2 and 2. Again, we can test, you know why we can test on the left-hand side of minus 2 and the right-hand side of 2, because of that restriction we had in that domain. So we only test in between minus 2 and 2, and you just have one concavity, so it's concave downward, all right? Is there any inflection point? No, obviously you only have one concavity, therefore there can't be inflection point. Inflection point, remember, you need a change of concavity from concave up to concave down, or from concave down to concave up. In this case, it's no inflection because there's no change in concavity. And the sketch is the easiest one. You just need to label in your vertical asymptotes. And then the next thing is your intercept. Notice that you have plus or minus 3, and then find where you had that turning point. Remember, that turning point is what I told you before, is your local maximum. Local maximum tell you where you had the turning point, and then the shape becomes obvious. You want concave down, therefore it's going to pass through those point of intersection, and then it's going to cut again there, and then gets closer and closer to the asymptote, it doesn't touch it. So this is one of the easiest sketches. All right. Now there's something called slant asymptote. Very, very important. You need to be very observant, all right? Because if you fail to make this observation, you might find yourself in a hot pot of soup. When I say hot pot of soup, it means that you find yourself losing so much marks for a very easy question just because you failed to make the observation. One, you get slant asymptote in a specific situation where you have a rational function and the degree of the numerator is just 1 more than the degree of the denominator. Very important. You should have a rational function and the degree of the polynomial of the numerator must be 1 denominator. You can see here, I have 3, and at the bottom I have 2. Slant asymptote. I can have 4, I can have 3 at the bottom, slant asymptote, 5 and 4, slant asymptote. So the difference must just be 1, all right? Then you know you have a slant asymptote. And then how do we do it? You use long division. Long division helps you to get this, all right? This is your quotient. Remember, because the degree of the top and the bottom, it differs by 1, it tells you that your quotient after doing long division has to be a linear function. Hence, you see I have mx plus b. When you do long division, you end up with your quotient just being a linear function of the form mx plus b. Now, to show that you have a slant asymptote, you just take the limit. So you need to show this. You need to show that you get 0. So this is something that you need to show, all right? Don't just say that y equals to that quotient is a slanted. You need to show y is a slanted. You take the limit as x tends to 0 of the function that I gave you, which is this piece here, or after doing long division, I'm going to explain, minus that quotient you got after long division, show that it's equal to 0. And then you conclude that y equals mx plus b is a slant asymptote. Let's do example 6 so that you understand slant asymptote. All right. This says sketch the graph f of x equals x cubed over x squared plus 1. Like I said, I make the observation that it's a rational function and the powers or the degree differ by 1. Therefore, I know in my head that I have a slant asymptote. So for now, I'll keep that in mind and I go ahead and follow the routine process, which is find the domain. Obviously, the domain is a set of real numbers. I'm going to explain why. Look at the top. X cubed is defined for any x value. But let's look at the bottom. X squared plus 1. All right. If you use b squared minus 4ac, notice that x squared plus 1 cannot be factorized. All right. So it cannot be equals to 0. Why? Because x squared can never be equal to minus 1. In that case, your domain is just x element of real number. All right. For intercept, you set x is 0, you just get y is 0. If you set y is 0, the only way y can be 0 is the top is 0, x cubed equals to 0, x is just equals to 0. Again, it shows you that your graph passes through the origin. Guys, these values for intercept and so on, they're important because it tells you where the graph is going to pass, all right? If you fail to observe that pass through the origin, you just go ahead and sketch some random stuff, you're going to lose marks. Symmetry, if you plug f of minus x, notice at the top there, minus x cubed is minus x cubed, all right? And then minus x squared at the bottom just remains x squared. I can factor out this minus sign and it looks like minus f of x, therefore my function is odd. All right. Now we know that function is odd. Is there any vertical asymptote? There is no vertical asymptote. All right. Why? I told you guys, we've done so many examples now. When your domain is the set of real numbers, it automatically means that you don't have a vertical asymptote. Vertical asymptote means there is a restriction in your domain. But in this case, look, there's no restriction. X is an element of a real number. It means I have no vertical asymptote. All right. But it doesn't mean that because I don't have a vertical asymptote, I don't also have a horizontal asymptote. You need to solve for horizontal asymptote. So you take limit as x tends to plus or minus infinity. And in this case, it gives you plus or minus infinity. In that case, it means that you don't have any horizontal asymptote. Now, some of you are wondering, why do I have plus or minus infinity? When you take limit as x, when we did limit, if you remember from 1a, when you have a rational function, we said we divide top bottom by the highest power of x, right? So I divide the top by x cubed, so I have 1. At the bottom, I divide by x cubed, I end up with 1 over x plus 1 over x cubed. Notice if you take the limit as x approaches infinity or minus infinity, you have 1 over 0, which is undefined. It's just something like that, plus or minus infinity. All right. So for those of you who have forgotten how to solve horizontal asymptote for a rational function, please go revise limits from Math 1a. Now here comes to the fact that you don't have vertical horizontal asymptote. You don't stop there. Remember, by looking at the equation, you noted on the side that there will be slant asymptote. Hence, show me that you understand that there will be slant asymptote. That's what I'm doing here. So I start by doing long division because I know there will be slant asymptote. If you do long division, notice you just have x. Your quotient is x, all right? And like I said, whenever I do long division, try and write it in this form. So you write it as quotient plus remainder over the divisor. So it's just x minus, remember this is minus x. So x minus x over x squared plus 1, all right? And your original function, so if you take this whole thing, so f of x minus that quotient that we have, it will just give you this piece here. All right. I hope that makes sense. So indirectly, it means that if I take this to the other side, remember I told you need to show me that it is a slant asymptote. You need to take limit as x approaches infinity of f of x minus that quotient. The quotient is what we got after doing long division. So f of x minus that quotient, I need to show that that limit gives me 0. Only then can I conclude that y equals to the quotient that I had after long division was actually a slant asymptote. In this case, let's see, if you subtract this, so this minus this, we've shown it already, is just this function here. And remember what I told you, when you take in limit as x tends to infinity of a rational function, you divide by the highest power of x. So we'll divide top bottom by what? By x squared. Notice it, notice it at the top there, you're just going to get 1 over x, and at the bottom you're going to get 1 plus 1 over x squared. All right. So in that case, you have 1 over x as x tends to infinity is 0, and at the bottom you have 1 plus 0. 0 over 1 plus 0 is 0. All right. So please go revise limit. Very important, revise limit. You can see we're now using L'Hopital rule and limits a lot. So please make sure you're very comfortable when it comes to limit. So the rule says that when I'm looking for horizontal asymptote, or in other words, a limit as x approaches infinity or minus infinity of a rational function, I look at the highest power of x that appears. Most of the time we focus at the denominator. All right. So the highest power of x that appears at the denominator. So if you look at this denominator here, which is what we're focusing on, the highest power of x is just x squared. All right. And let's assume that I had, I'm going to show you something so that I don't get confused with this thing. If you have x to the power 5 over, let's say, x to the power x squared plus some number, all right? And you need to find horizontal asymptote, limit as x tends to infinity. I know some of you are thinking that I'll divide top bottom by x to the power 5. The answer is no. I say you choose the highest power of x that appears at the denominator. So it means that you look at the denominator, the highest power of x is just 2, so it's x squared. So I divide top bottom by x squared. In this case, you notice that the limit will just give you infinity. All right. I hope that was clear enough. If you're not happy, then go revise your limit in 1a. And the conclusion is that because I have 0, that is what I want you to show, you conclude that therefore y equals to x is a slant asymptote. All right. First derivative, we need to do increasing, decreasing. You get this. Take note, the only way this can be equal to 0 is if the top piece is equal to 0. In that case, you just have x equals to 0. Remember, x squared plus 3 can never be equal to 0, right? Because x squared cannot be equal to minus 3. That doesn't make sense. You can't square a number and you get a negative result. And this, x squared plus 1 also can never be equal to 0. It means that this function, there's no way of which it is undefined. So in that case, your only critical value is 0. Now you test. So we test using minus 1 and 1. In that case, you get that is increasing on both sides. All right. It's increasing on both sides. Very important, because my domain of the original function is a set of real numbers, I can test using any number. There's no restriction of the number that I can plug in. All right. Now we've seen that it's increasing on both sides. What does that mean? It means that you don't have, so first of all, tell me your increasing, decreasing happens from minus infinity to infinity. Now this is a very exceptional situation where I include the whole interval. I'm going to explain why. It was increasing on both sides of 0. All right. So one student will say, for it increases from minus infinity to 0 and from 0 to infinity. All right. It's true. It's fine. But remember that the domain is a set of real numbers, meaning that the function itself is defined at the point x equals to 0. Hence, I can just conclude by saying that it works from minus infinity to infinity. But again, there's no harm if you choose to split it into 2. So I will still give you full marks if you say from minus infinity to 0 and from 0 to infinity. All right. But for those of you that are quick enough to see make that observation, that the function itself is defined at 0, since the domain is a set of real numbers and we don't have any vertical asymptote, it means it's increasing everywhere. All right. That's just what the conclusion says. It's increasing everywhere. So please make that observation and see that it's increasing everywhere. All right. The reason why we choose to never include this x value, because most of the time where there's increasing and decreasing, there's usually an asymptote at that point, meaning that the function itself is undefined at that point. But in this case, the function is defined at that x value. There we have no local max or local min. It makes sense, right? Because it's increasing on both sides. For you to have local max or local min, there should be change in increasing and decreasing. We go to concavity, as usual, second derivative. I told you before that before you do your second derivative, go and check to make sure that your first derivative function is correct. So do the first derivative again on the side to see that it's correct. By doing that, you might even spot an error and you can go back and fix your increasing, decreasing. All right. So that's why step 7 is very critical, that you go back and test your first derivative. If you get to the same answer, it means what you did for increasing, decreasing, and local max and local min are correct. But if you test again for the second time and you get a different first derivative, it means that you don't want, you save yourself losing marks, because you can go back and redo your increasing, decreasing, as well as your local max and local min. All right. So always test. So once you do first derivative, it's fine. Then you go ahead, do the second derivative, simplify it as much as possible. You see there, factorize. I factor out minus 2x. Notice it, this can only be equal to 0 if the top piece equals to 0. If I equate the top piece to 0, I get x is 0, and I get x is plus or minus root of 3. Now, this bottom piece here can never be equal to 0. Why? Because we said b squared minus 4ac is typically less than 0 there. We call it irreducible quadratic function. All right. Once you make that observation, you notice that there's nowhere where the second derivative is undefined. Therefore, these are your only critical values that you need to work with. All right. Plug them on the number line. You see that there's a lot of change of concavity. So there you have concave up, concave down, concave up, concave down. All right. And very important with testing using the second derivative function, not our original function. So tell me this interval of concavity using union, not intersection. Please use union. All right. You can't say intersection because intersection means you're joining the two. If there's one piece here and there's another piece right here, look what happened in between here. All right. There's nothing in between here for your concave upward. So you have to use union. If you use intersection, it means that they lie side by side. All right. Another word for intersection is just saying that I can as well just merge them. It's actually equivalent to the example that I did for increasing and decreasing, where I say the increase from minus infinity to 0 and from 0 to infinity. In that case, it's an intersection. All right. And intersection hence means you can join them. That's why I end up just saying is from minus infinity to infinity as my interval of increasing. All right. I hope you won't make the mistake and use intersection when you're dealing with concavity, especially in this case where there's nothing happening in between them. All right. So concave up happens there and there, and you see in between here there's a whole gap where there's a different concavity. So in that case, you use union, not intersection, because you can mesh the intervals. All right. Clearly, you can see that there are two. Are there two inflection points or three? Okay. You don't have to tell me. I know you know that there's 3 inflection points. Look at it. At minus root of 3, there's change of concavity. At 0, there's change of concavity, and at root 3, there's change of concavity on both sides. Therefore, you have 3 inflection points. There you go. F of 0, 0, F of root 0. All right. So those are all inflection points. You need to solve it exactly the way I'm doing it. Don't go in the test and give me something funny. X equals to 0 is an inflection point. I'm going to ask you, is x equals to 0 a point? Like what? It's a value, all right? A point is x and y coordinate. When x is 0, y is 0. That's a point. So inflection point looks like this, 0, 0. All right. So either you write it as 0, 0, or you just leave it as f of 0 equals to 0. You've given me a point there where x is 0, y is 0. All right. Now to sketch this, as usual, label your x and y. Although mine you don't see x and y, don't imitate me. Make sure you put x and y so that I know that what reference you use it. If you swap them around and you use this other side as x and this one as y, it's fine. I'll just rotate it around and I know that is your reference. And next thing, put your asymptote. We only had a slant asymptote. Notice it? That's my slant asymptote. Is that line y equals to x? That's my slant asymptote. All right. And we notice that for intercept, your curve passes through the origin. So mark the origin and know that the curve needs to pass through the origin. All right. Now ask yourself, where do we have turning points? Where do we have the local max or local mean? Was there any local max or local mean? The answer is no. There's a reason why if you look at this case here, there's no turning point. However, you have inflection point. Inflection point, you need to label them. So label every point. Label the point of intercept, label the point of local max and local mean, that's your turning point. Label your inflection points. Always label them on your sketch. Why? Because I'm going to see that you sketch in the right style. Now that you have your inflection point, you look at your concavity. With your concavity, then you're good to go. We know that from minus infinity to minus root of 3, there was a concave up. That's why you have that kind of shape there. And then from minus root of 3 to 0, we have concave down. And you know it has to pass through the origin. You have that piece there. From 0 all the way to root 3, you had concave up. Again, you see, that's why you have that shape there. And then from root 3 up to infinity, you have concave down. Hence, that's why you have that shape. You see, your curve gets closer and close to the asymptote every time. And that's how easy it is to sketch this graph. All right. That's basically it. Go practice. There's more example here. I've uploaded your TAT. They're now available on Blackboard, including the memo. So practice, see if you can get those 3 sketches in your TAT correct, as well as this example as well. And yes, that's basically it from my side. Is there any question? Now you can ask your questions.